presentation right now, yes?
Yeah.
Yes.
Okay, good. All right, so as Garth said, this is the third presentation that we've done in a sequence. The first two focused on our online interactive program for setting up the functionality. This one's going to focus on the actual simulator itself and some functionality that isn't accessible through that online interface just yet. So 6X is a general purpose reservoir simulator, but it has some specific functionality that provides an unconventional solution for horizontal fractured wells, putting the geomechanics and the fracturing and the simulation of the flow into a single model. So what we'll look at, why do people do unconventional simulation? What are their objectives? How does 6X do that differently? And we'll look at various aspects of the program to show that. And we'll also talk a little bit about how 6X fits into a workflow, so how you can use the online interface that we have, how you can use third-party products with it, and so on. Okay. So objectives of unconventional simulation, the kind of things that we're addressing here are development planning things, such as the number of wells, the spacing of the wells, both vertically and horizontally, how they interfere with each other, how you can judge the amount of interference by varying the spacing and also by varying the size of the fractures, the half length, the extent of the SRV, etc. Of course, if you do a bigger job, then the SRV goes further. That impacts the decision on the spacing. You can look at infill wells, how they impact parent wells, refracturing wells, and you can also look at things like designing huff and puff strategies, rolling out pilot programs through to full field designs. Those are the kind of workflows that we're looking at addressing here. And the one thing that they have in common is that you really need to be realistically representing how the wells are going to interact with each other for any of that type of design work to make sense. So the traditional approach to doing unconventional simulation is essentially to bolt together a frac design software and a reservoir simulation software.
Pete, time.
Okay, I think I just unmuted myself.
Oh, apologies, Pete. That was my fault.
No problem. So the frac design software is generally very good at designing fractures, determining the operational procedures, the amount of chemicals and sand and fluid and so on that are introduced into the well to build out fractures. And the reservoir simulator is probably very good at doing production prediction. But the process of joining them together requires you to wrap the frac design into a simulation grid and then proceed from there, which kind of introduces some difficulties. So you have to merge the frac design for multiple different wells together into that simulation grid if you want to do an entire a pair of wells or an entire section of wells. Generally, the simulation part of it happens after the frac has been introduced. So you design your frac in the software and then you wrap a grid around it, and then you have to define on that grid where the fluids exist, where the pressure exists, somewhat artificially, so that you have a realistic starting point for your production simulation. And that adds in some user choices as opposed to it flowing naturally from the injection of the frac fluids. It also, if you want to incorporate geomechanics, if you want the stresses to change during the process, that will probably require adding in a third piece of software, which is linked with the reservoir simulator, where the simulator passes across pressures. The geomechanics finite element software passes back changes to permeability, to stresses, etc. So this is, it's a somewhat clunky design of a workflow. So what we do with 6X is we have a single model, and that model incorporates the geomechanics, the frac design, and the production. All of that happens together on a multi-porosity simulation grid, which can be a full-featured geological model with faults, etc., etc. It doesn't have to be nice and plain and flat like the one in this picture here. So we do all those stress and flow dynamics together on a multi-porosity simulation grid, and we integrate the geomechanics, the changes to the stresses, on there as well. So it's all solved together. So we don't use a discrete fracture network as an input. We capture basically the underlying aspects of the natural fractures in the background grid properties on this multi-porosity grid. We represent the frac growth through that grid by enhancing the properties of the grid. So changing the permeability, changing the interface between the fracture parts and the matrix parts of that grid. We then have hysteretic reduction of those enhancements to model the closure as the model is depleted. So we have all of this happening simultaneously within a single simulation grid. So if we look at some details of that, we've got our simulation grid, we've got our well locations, we open a stage which is represented by a series of clusters, perforations in part of the well bore, and we inject fluid, we simulate the injection of fluid into that well. The fluid goes to the stage location and flows out into the grid at the cluster locations. And we pump each stage in turn. So we open the well, pump into it, close it, open some new clusters, pump, etc. So this diagram here is showing the bottom hole pressure as it peaks while we are pumping, and then it declines as we prepare the next stage, and then we pump that, and so on. So this captures the fluid in the model. The leak off is captured by tracking how it leaks off from the fracture system to the matrix system, and it captures the pressure, the energy in the system as well. So as the fluid enters the simulation grid and it increases the pressure, we model the rock breaking by tracking tensile and shear fracture enhancement. Now, the way that that works is if we look at a single cluster along the well, we can plot what happens there on a graph like this. So here is our well bore at our particular cluster location. The y-axis is the pressure, also the stress. And the x-axis is the distance away from the well. So we're going to start off at the initial reservoir pressure with a positive net stress. We're going to use the input minimum stress and use that to know when we are achieving breakage, which is going to be when we have a negative net stress. So as we pump at this location, the pressure at the well bore is going to rise. That pressure is going to push out into the reservoir, and ultimately it's going to breach the input minimum stress so that we have a negative net stress. So once we've got a negative net stress, then we're breaking the rock, we're adding in tensile and shear enhancement to model that enhancement. So any place where our pressure has pushed out to the point that we have negative stress is going to be part of our SRV. And within that area of the simulation grid, we're going to have additional shear complexity and additional tensile fracturing in terms of permeability and interface between the matrix and the fracture to represent the aspects of that SRV, the complexity and the tensile breakage. The distance out into the reservoir that we reach with that negative net stress is going to be the half length at that given location of our fractures. So that's going to give us the extent of our SRV along the well bore. So that's just one point along the well. We are modeling lots of those simultaneously to capture all the clusters within a stage, and then we're modeling the clusters within the next stage and so on until we build up a representation of an entire SRV along a well, and we can then pump the next well after depletion, and we can track how that next well interacts with the first one. And we can do this for multiple wells across entire drilling units, across whole sections within our geological model. Okay. Now, the assumption there was that that input minimum stress remained static throughout that process. In reality, it's going to change. So to track how that changes, you can optionally use the built-in poroelastic equation to update either the mean stress or the full directional stress tensor. So this poroelastic equation is coupled and solved together with the flow equations. It's based on the TUF2 formulation, and it uses geomechanical properties, Poisson's ratio, etc., to calculate how the stress changes based on the changes in the pressure. And that allows us to derive a dynamic net stress from the input net stress. Okay, so if we look at our picture again, here's our cluster location. As our pressure increases in the reservoir, the stress also increases. The rock becomes a little harder to break as we push on it. The pressure catches up with the updated stress and exceeds it. So with the poroelastic equation in effect, we end up with rock that's a little harder to break while we're pushing it. So we have to go beyond the initial net stress, and we get a more compact SRV, a more realistic SRV. Of course, this is what happens to the stress when we are pushing fluid in. When we draw fluid out, we have the opposite effect, and the rock becomes easier to break because the stress reduces with the depletion. So there's an increase in stress during pumping and a reduction in stress during depletion. If we use the full stress tensor, then we can see the effects of this on the propagation of the fractures as the well is pumped. So if we look at the frac on the left here, this stage here is symmetrical from one side to another, but the fractures, the outermost fractures, have progressed further out from the well than the innermost one, because the stress shadowing effect is limiting the inner clusters. Then when we pump the second stage, the clusters that are close to the existing stage are impacted by it and don't propagate as far as they may otherwise have. The ones that are further away propagate further. So we get this stress shadowing effect echoing along the well from the toe to the heel. Okay. So we can use all of those effects to, as I said, model how wells interact with each other. So here we've got a pair of wells, and we're going to fracture the first one. So if we look right here, we can see where the first clusters are initiating fracturing within the simulation grid. Here we've filtered what is visible to show just the cells where the breakage has occurred. So we've initiated fractures at these clusters, and as we keep pumping, these fractures will move out into the grid in 3 dimensions and will form an SRV. So if we forward from there, we can see how each of those is growing and linking up to form that first stage. And then the other stages of the well will be completed as well. In this example, we've just got 4 stages, just so we can illustrate what's going on. And you can see that the stages are not homogeneous. There are different extents to them vertically and horizontally based on the properties of the geomodel and the shape of the well and how it passes between different strata. Okay, so there's our first well completed. Let's assume that we're going to deplete that well. We're going to flow back the frac fluid. We're going to produce and reduce the pressure for a while. So if we plot what that looks like in terms of the SRV and the frac fluid saturation, might look something like this, where we've got essentially no frac fluid left, which is the red color here. So then we complete the child well over to the side here, and we can see how, as we start to complete that, the frac fluid will preferentially flow towards the parent well. So this rock over here is already broken and weakened by the fracturing and the depletion. So the frac fluid is finding it easier to move over here. So we're dynamically capturing the interactions between the wells, and we are not forcing the fractures to go in any particular direction. We're just changing the underlying characteristics of the geomodel to capture the effects that we want. So we're calibrating the underlying aspects of the model to get the dynamic behavior that matches our history, so that we can then use that dynamic behavior as a predictive tool. If we look at the plot of what's going on at that parent well, this top graph here is the pressure, the next one is the water saturation. And so if we plot those characteristics against time, we can see where we have high pressure at the beginning, where we've got the fluids being pumped to fracture it, and then we've got the depletion, and then later on we've got frac hits which come in and cause a bump in the pressure and in the fluid, in the water production. These little gray blobs here, which hopefully you can see, are historical observations. So this model has been history matched to reasonably match the behavior of the actual well, so that we can reproduce the real world behavior in our calibrated history matched model. Okay. And so once we've got a model where we can reproduce real world behavior, we can use it for experimental purposes with some confidence. So this particular experiment here, we are setting up an enhanced oil recovery program. So over here on the left, we're doing a model with a single well where we are injecting, soaking, producing, and we're repeating that cycle over and over again. And we can experiment with different pumping pressures, pumping durations, soak times, etc., to work out just what the optimum phases are. So if we look at that on an actual real world example, over here to the left, we've got the initial fracturing of the wells and the depletion of them. And then we've got our EOR processes kicking in. So we've got boosts in the amount of production on a cyclic basis. Now, one workflow feature of 6X is that you can run the model either black oil, or you can run it compositional with an equation of state to define the fluids. Equation of state-based modeling is quite expensive in terms of runtime. So one thing that we have is the ability to do part of the run in black oil mode, and then to flip to a compositional state, so that you've got a set of components and equation of state that determine what's going on. So it needs to be compositional if you're injecting something like CO2 or non-reservoir gas, etc. So that's why we can do the black oil for the base model, and then for the predictive part, we can switch to compositional. And that's a workflow feature which is easy to do. Another thing which is worth mentioning is that the black oil and the compositional are all part of the same 6X license. You don't have to buy additional add-ons for any of this stuff. It's a single license that covers all of the functionality. So if we look at our drilling unit, here's our the wells that are involved in our enhanced oil recovery program. And so we know from our history matching of our base model, our initial production, what the fracture channels should look like, what the SRVs should look like, and how the wells are connected. So we can use this to predict the conformance of the injected gases. So we can work out which wells should be shut in, which ones should be producing, which ones should flip between injecting and producing. And we can experiment with different combinations and different schedules, and we can predict what additional recovery we can get from each of those scenarios. So up at the top here, we've got the different oil recovery amounts. At the bottom, we've got the net gas production. So if we just keep producing, the net gas production always goes up. If we're injecting and producing back, then it goes up and down in a cycle. So if it's important to us to hide away some of our gas production, then it may be just as important to know which type of cycle gives us the most gas injection as opposed to the most oil production. Now, doing schemes like this, where you've got a lot of wells involved in the model, and some of those wells are producing at very high pressure and then, injecting at very high pressure and then producing down to low pressure, is a very difficult problem to solve in terms of the simulation process. So it requires a very stable, very high performance simulation infrastructure to be able to support that. So one of the design features of 6X is that it is built to be massively parallel. The runtime scales well as you add more resources, the latency is low, and also we can run on either CPU cores or on GPUs. So over here on the right, we've got a comparison between a single core down to a 128 core run. So as you add more and more compute power, you can go from maybe a 10-hour run for a zipper frac model, such as we're animating here on the side, down to maybe 15 minutes or so. So you can do that by adding a lot of cores, or you can use a GPU, such as an NVIDIA A100 or V100, and get a similar kind of speed up on a very economically accessible type of hardware. These multi-core systems are very expensive, but very effective. GPUs are very effective and relatively cheap compared to big multi-core clusters. We can also make the run go faster by doing dynamic upgrading. So we have the option to specify the area where our wells are to keep that at very high resolution and to coarsen the rest of the model where there's less activity. So this works by factors of 2 by 2. So each block of 4 cells at the lowest resolution or the highest resolution will be combined into a single cell, and then further away sets of 4 of those cells will be combined into a single cell, and so on, to get this patchwork effect. This happens automatically. You don't have to describe how the properties change. You don't have to recomplete where the wells are. You just tell it, I want this area coarsened or this area refined, and it does it for you. So the upshot of this is you can get consistent results, but you can get them significantly faster because you're replacing whole swathes of very small cells in areas of little impact with much larger cells. In terms of model throughput, we've got built-in multiple realization workflows. What this lets you do is set up all of the multiple realization type workflows that you might do through an interface such as Petrel RE or Enable or something by describing those workflows that you want with keywords in the data set itself. So a simple set of keywords let you set up the workflows you want, the variables you want to use, the way to combine those variables, and then you replace actual data in your model with the name of the variable, and 6X will substitute in the sample values and spawn off multiple copies with different sample values in, so that you can run several copies off of a single model. And you can do all of those, if you have the hardware, you can run several copies of the model simultaneously with a single license. So if you have 16 different experiments that need to be done, you can set it up in such a way that those run simultaneously and use just a single license. Okay. So getting the model set up, as I said, one way you can do that is you can use the 6X online program, which we talked about in the previous 2 demonstrations. Those are accessible from our website, by the way, if you want to go back and look at them. And this supports a limited amount of functionality on a layer cake model, but it lets you quickly set up a model, run it, evaluate the results, and then you can export that model and you could substitute the layer cake model that was built by the online tool with the real geological model from Petrel or wherever your models are built. You could add in additional functionality to make that model more sophisticated, building on the underlying characteristics that were set up in 6X online. That actual data can be Eclipse compatible. So if you know the Eclipse keywords, or if you have a tool that can generate Eclipse keywords, you can use that to generate 6X models. It's editable plain text, so if you understand the keywords, you can make changes just with a text editor. In addition to the basic Eclipse compatible keywords, we've added in keywords that allow you to bring in JSON formatted data. So things like field unit, well descriptions, well trajectories can be brought directly into 6X as JSON formatted data, which you can generate with Python or something, or in 6X online. And those trajectories are in XYZ data, like straight from the field. You don't need to convert them into the IJK cell locations on the geomodel. 6X will do that for you based on its understanding of where in space the model is. So you can combine all those things together. Your knowledge of Eclipse compatible keywords, the data which can be generated from 6X online, and also data which can come from Petrel or Python or wherever. Okay. For the results, we also generate Eclipse compatible output files. So anything that works with Eclipse type results can also work with 6X. So that includes Petrel, ResInsight, Coviz, TechPlot, etc., etc., etc. In addition to that, we also output web-enabled data for line plots. So we write HTML files and JSON files, which allow you to do line plotting directly from the 6X output in Google Chrome or Microsoft Edge or wherever. You can also read that JSON data through Python or whatever into things like Spotfire and display the results there. It's very flexible. Okay. So that's how we get data in and out. So to summarize what we've said here, 6X is the flexible solution for unconventionals. It combines geomechanics, hydraulic fracturing, and flow simulation in a single model. So the fracture generation comes from the pumping schedule and the impact that that pumping schedule has on the stresses in the model. You can combine that with a full stress tensor poroelastic solution, and you can do the fluid modeling in either black oil or compositional mode, or you can combine the two. It's high performance, which allows you to solve these very demanding models in a reasonable amount of time. So it's massively parallel, it has efficient nested refinement and coarsening, and you can spin off multiple versions of a model to solve simultaneously. It has industry standard data input and output, which is compatible with a wide range of industry interactive tools, some of which are free to the user. So it supports what we think is a superior field planning workflow, linking the fracture design to the production to do single well modeling, parent-child modeling for well spacing and interference modeling, and all the way through to enhanced oil recovery modeling, which supports your management decision-making for the well count, the spacing, your completion strategies, and your enhanced oil recovery strategies to minimize the number of wells that you have to drill and to maximize the effectiveness of those wells. Okay, so that's really all I have. My name's Peter Foster, and if you have any questions, now would be a good time to ask. Very quiet.
Right. Well, Pete, I have one question that came directly to me, and it says, what are the main features that have described that are not available in the UI version?
Well, at present, the UI does not have a button to introduce the geological properties and to switch on the full tensor solution. It also would be slightly challenging to set up an EOR kind of cyclic injection production through the user interface. It would be possible, I think, but it wouldn't be the easiest way of doing it. So yeah, those are really the main ones that are not in there.
So there's another question, and I guess it sounds very similar. How do we add structure to the model? So I guess we're looking at, what does importing a geological model mean?
So if you were starting with the user interface, it allows you to specify, I don't know if you can see this, but basically it lets you specify the depth and the thickness of the layers. So you end up with a flat square model. There are a couple of keywords in the data set that says, this is where the top of the model is, this is the extent of it, this is the thickness. You could take those out and put in an include statement that pointed to a file exported directly from Petrel in Eclipse format, and that would bring in the geometry and the geological properties directly from that model. The wells that you defined within the user interface are defined using this JSON format that we use, which means they're specified in X, Y, Z locations. So 6X can automatically work out where on the new geomodel those wells are going to land and automatically complete them for you, so you don't need to have an understanding of which grid cell it lines up with in terms of the IJK index. Does that make sense?
More questions on the Petrel angle. So is there a Petrel connector, or is the potential consideration for the future? So I guess it's probably worth explaining that because we're so Eclipse compatible, that you can essentially run a model straight out of the box if it's a nice simple Eclipse model.
Yep, that is true. So yeah, the only keywords or the only pieces of data that are not the same as Eclipse pieces of data are the tables that define the enhancement in terms of how the net stress links to the additional permeability and the initial fracture matrix interface. Those would be relatively easy to add in as user keywords to a defined Petrel model outline, case outline.
So
I guess if that did turn out to be an issue, we could add in a macro to do that for you, a plugin, I guess it would be called. But at the moment, we haven't seen the need to.
Well, I'll carry on reading these out, though people are more than welcome to jump in and ask their own questions. So here's one, Pete. Have you verified the fracture lengths and heights with a standard frac simulator?
Yes. You can tune the inputs to 6X to match the outputs from Gopher or Stimplan or whatever. Yes, we have had people do that, and you can match essentially.
I guess we had one client in particular that did do a study with, now I'm trying to remember the codes, but ResFrac and
Stimplan.
And they were able to produce very similar looking SRVs, is my takeaway from that work. Do we have plans for modeling injection of proppant as well? Yeah, you got to answer that, Pete, or
I'll let you do that one.
So we have more than plans. We have fairly extensive proppant modeling features. So essentially, you can treat proppant as a tracer that is solved at the end of a time step, and initially it will go in with a fluid and follow the fluid around. And then there's a number of models about what happens to that. For example, proppant will settle under gravity, so it will move downwards preferentially as gravity takes effect. I guess my impression is that it's quite challenging, shall we say, to know where proppant actually does go. So we have a range of models, and you've got quite a lot of ways of describing that proppant. Very difficult to prove which ones are accurate, if you like. Ooh, we've got lots of questions here.
Yeah, I'm just kind of zooming back through these. There are several. Have you verified? Yep. Yeah, okay, so that's where you got to. Can you expand a bit on using it, including some of the overburden for a large frac of a vertical well, for example? We have had people use this to model fracturing vertical wells. And yeah, I don't know, not quite sure what detail you want there, Isaac.
I missed that one.
It's, I mean, if you, no, I sent that only to Peter. Scared of you, Garth. But I mean, since you can do the geomechanics on properties on cell by cell, I assume, then you could use it in principle if you put the right properties to see whether the frac is going to get out of the reservoir and stuff like that, at least within the constraints of the parameters you provide.
I think yes, indeed. In fact, one of the tricky unknowns of models I've seen is knowing, where does it go vertically or does it go out, and that there are parameters in the model that let you describe how that happens. So, for example, if you're doing the carbon sequestration problem, you're worried about caprock integrity. We can tackle that kind of problem, at least trying to understand it, and then how you verify the simulator results is as usual a challenging question.
Okay. So another one here, the SRV is calculated by the simulator. How to match production of each well for a multi-well model. So the main thing that you calibrate is the way that the net stress and the amount of enhancement are linked. And you can supply tables that represent that on a single one, or you can provide them on a layer by layer basis. The assumption is that if in a particular layer the rock breaks in a certain way at well 1, then all things being equal, it should break in the same way at the well 2, at the child well, give or take any lingering after effects of the fracturing and depletion of the parent well. So if you have a single well with observations, you can calibrate your model based on that, and it should give you a fighting chance of getting a realistic answer for the second well. If you have the results for a set of wells, then you can do more rigorous calibration, and you can calibrate based on how each of the wells produce, but you can also calibrate based on how they interact, as we saw on that line plot. We capture the interaction between the wells, so you're not just calibrating on what's happening close to each well, you're calibrating what's happening within the system between the wells. And that generally that means that you're changing that relationship between the amount of net stress, the amount of permeability enhancement in different directions, and the amount of shear enhancement, the interface between the matrix and the fracture, the amount of leak off. So usually calibrating those things should give you a model which is consistent for all the wells. An eGrid format will work. Yes, you can include zcorn and coord keywords, or you can import, I think the keyword is, if you use an eGrid file, something like that.
No, I think we can import them directly, yeah.
Yeah, we haven't tried PEBI grids. I don't know. I'm not sure why we would do that unless we were just trying to duplicate what something like Intersect was doing directly. But we would rather, rather than doing that DFN based fracture propagation followed by PEBI gridding followed by simulation, we prefer our workflow as an alternate for that whole thing, if that makes sense. What kind of linear solver are you using? Garth, Ian, you want to have a shot at that?
Do you want me to have a go at that one?
We'll let Gareth do
any
that
of the above.
So it's what's become fairly standard these days in reservoir simulation. I think it's basically an orthomin solver with a CPR preconditioning, and the CPR preconditioning uses a multigrid solver for the first stage. The complication is that we want to implement this, as you've seen, on a wide range of platforms. So it's got to be compatible with CPU, multiple CPU clusters, and GPUs and clusters of GPUs. So that makes the development of the linear solver a little bit more complex, but we've designed it in such a way that it'll give you the same answer regardless of what type of platform you're running on. That was the idea.
I guess, Gareth, the other thing you could mention is that you've extended the CPR because of the stress equation to handle that a little bit more.
Oh yes, of course. Yeah, that's true. Yeah,
worth mentioning.
Would these produce only planar fractures, only straight fractures? Generally speaking, yes, the fractures are going to follow the gridding. The grid resolution should be fine enough to capture how the fractures propagate from each stage or cluster or whatever resolution is appropriate for the type of answer that you're getting. Because we're on a simulation grid, we're modeling the effects of the fractures at a gross level, not massively coarse. We're talking maybe 10 foot by 30 foot, something like that. So unless the fractures were to deviate enough that they went diagonally on that kind of resolution, then we're getting them, we're capturing them. If they were deviating that much, then that would be an issue for us and we'd have to think that through. However, generally speaking, there's enough of a contrast in the stress so that the preferential direction can be captured sufficiently to give a realistic model. Okay. Let me know if you need to talk that through for a specific case or something in more detail. Yes, we can handle faults. We can handle fractures and other structural features. So the grid that you supply 6X can have layers that change thickness, that pinch out, that are dislocated so that there are representations of faults, and on one side of the fault you have layer 3 which lines up with layer 6 on the other side because of a dislocation. We can do all of that stuff. Any existing fractures can be represented by the baseline permeabilities that we put in, up to and including having a dual permeability model if necessary, where we don't just have connections at distance through the fracture system, but we have direct connections between matrix blocks, which is something that we've done for a couple of places in the world. Hopefully that answers that. do you consider perm change in the SRV with the swing of reservoir pressure? I think the answer to that is we have closure parameters which are hysteretic and are triggered by changes in pressure and can optionally be tied to whether or not you have a negative net stress. So those enhancements that we put in will then decline with pressure as you deplete. I think that answers that. Can you simulate stress change during well production? Yes. So what we showed there was the stress stiffening as we inject. The opposite effect of the stress relaxing as we produce also happens by the same process, this fully coupled poroelastic solve. And that can either be a change to the mean stress to capture just the weakening, if you want to call it that, of the rock, or it can be the full tensor to capture the directional changes. Okay.
I think the answer to this one is yes, in that if you've got a very shallow formation, you're at liberty to define your initial stress state such that you end up with horizontal fractures. So we would then end up with enhanced permeability in X and Y and not in Z, if you see what I mean, which I think you could think of as bedding planes having been lifted.
And can you share the recording? Yes, the recording will be placed on our website, which is here. And the previous two presentations are also on there, along with links to useful UR Tech papers and so on. Okay. Anything else?
Anyone want to jump in with a question verbally? I guess not. We've exhausted them.
Okay.
Okay.
All right. Well, thanks for listening. If you want to contact us, feel free. Open to any follow-up questions. Other than that, I think that's us done for the day. Okay. Thank you.
Okay.
Thank you, guys.